Okay, so reflections. Yeah, what about reflections? One of the types of transformations we talked about. What do we know about these things? We know that with a reflection, we've got this line that acts like a mirror or a fold in the paper, however you want to think of it, right? Either we're going to be reflecting stuff in a mirror, the line that's a mirror, or we're going to be drawing something on one side and then folding the paper to create an image on the other side. AJ, turn face front, focus, thank you. We call the mirror or the fold in the paper the line of reflection, okay? And the terminology we use, we say that something is reflected in the line. It's not reflected over the line, even though it seems like that's how we ought to say it. Geometry, we use the wording that's reflected in the line. So you saw stuff like this on Geometry Sketchpad the other day. A reflection in this line, it's supposed to be line M, I'll label it M, is a transformation that maps every possible point P, pre-image P, onto an image P prime. Now, P could be just a single point here, or it could be one of a whole bunch of points that make up a more complicated shape. For example, what if I wanted to reflect, I wanted to reflect the letter S over this line, right, to create an image from that pre-image. It's going to look something like that if I do that. And the blue pre-image is just a collection of how many points? Probably even more than 2. How many points are there on that blue S? So how many would it take to make that whole shape? Millions? More? Infinite, yeah. There's an infinite number of points that are linked together. Each one of those infinite points is going to be treated using the same rules as this single point P, right? So I could focus on just the point P, or the point P might end up being just one point that gets mapped, one point of an infinite number that gets mapped from the blue to the red with these letters too, right? So just because we're talking about a single point doesn't mean that this doesn't apply to larger shapes too. It does, because they're just, you know, sums of many points. All right, so these are the rules. And you sort of identified this stuff yesterday. In fact, you tell me about this. I won't tell you. Based on your observations in Geometry Sketchpad, if we focus on these 3 points, point P, point X we called it, I think, and point P prime, and maybe we'll add one other point. Let's call that point A, how about? What are some measurements, some things that you found when you played with Geometry Sketchpad and you made some measurements? What were some relationships that were true? What are you doing? Put that away.
I am. I'm finishing off my sound.
Ah, okay, good. Yep. Okay, so what are some relationships we got here? Yes? Ah, okay. There's one important thing. Good. We found that the distance from P to X was always the same, was equal to the distance from P prime to X. So we could say that segment PX is always congruent to segment P prime X, right? That was one important thing. There's one other important thing too, hopefully you saw. What do you think, Scott?
Line reflection, line between the 2 points.
Okay, we measured this angle, PXA, and we found that it was always 90 degrees. So if we combine those two things, what that tells us is that if we think of the line connected, the segment connecting P to P prime, right? So let's just focus on just that one thing. So here it is, right here, this segment. That segment, the line of reflection is always a perpendicular bisector of that segment that connects the pre-image and the image, right? Perpendicular because they meet at right angles, and a bisector because those distances are the same. Okay, that's always the case. Now there's the other case we have to consider though, is what if point P is not separate from the line of reflection? What if it actually sits on the line of reflection? So what if this were point P right there? Where would P prime go now? What do you think? Same spot, right? That's like putting the dot of ink right on the fold in the paper. When I fold the paper, does it move?
No.
It stays in the same spot, right? Okay, so if P is on line M, then P and P prime, the image and pre-image and image are the same thing. Okay, so what about these? Let's look at some reflections. Now we're gonna start off here focusing on simple reflections. We're gonna focus on reflections over horizontal and vertical lines. So what's gonna happen if first of all, if I want to reflect point H, which has coordinates 2, 2, right? I want to reflect that in the x-axis. So let me draw the x-axis so everybody can focus on that. Here it is, right here. Right? Okay, there's the x, and what this little symbol means, it means that I can kind of twist things or reflect things around that. Does that make sense? Okay, so I'm going to take this point and I'm going to reflect it over that line. Now, where is the image of that pre-image going to end up? AJ, last one. Don't talk, focus on the front. If you have questions, raise your hand, but that's it. Those are your limitations. Yes? Say it again? 2, -2. Good. So we're starting off at the point 2, 2, and when we reflect it, it ends up down here at the point 2, -2, right? And that has to be the case, doesn't it? Because that's going to make the segment connecting H and H prime perpendicular to the line of reflection, and it's going to make the line of reflection run right through the middle, right? Now, if you had to describe this process to, let's say, a grade school kid or something, you want to tell them, anytime I reflect a point over the x-axis, what's always going to happen? I think there's probably a pretty simple way we could always make a prediction. What's going to happen? What do you think, Nick?
The x coordinate is going to be the same.
Okay, the x-coordinate's always going to stay the same. Good. What's going to happen to the y-coordinate?
It's going to change.
It's going to change how?
It's going to change from a positive to a negative.
Okay, they're going to be opposites, aren't they? They're going to flip between opposites. Now, I want you to think about, rather than try to memorize that as some kind of a formula, because you'll just forget it, right? Those stay the same, and these become opposites. I want you to think about this sort of conceptually or visually, and then you'll remember it. If I'm going to reflect a point over a horizontal axis like that, is the movement of the point from its pre-image to its image going to be vertical or horizontal? If I'm folding it over a horizontal fold, is the movement of the point going to be vertical or horizontal?
Horizontal.
It's going to be vertical, isn't it? Right? So if it's going to be vertical, then we would expect the...
That's what I thought I was giving it back.
Okay. We would expect the y-coordinate to be the one that changes if the motion is vertical, right? Does that make sense? Because the y-axis is the vertical one. It's not changing horizontally at all, right? The 2 points are always going to line up horizontally if we're folding them over a horizontal axis. And so we would know then that the x-coordinates are going to stay the same. It's the y-coordinates that are going to get flipped, right? Now, what's going to happen if I fold something over a vertical axis? And let's specifically say the y-axis. This time I'm not going to give you number points. I'm just going to give you, I'm going to call this point UV. So I don't even know what the numbers are associated with that point, what the coordinates are. Okay, but what would the coordinates of the reflected point be? What do you think?
Negative u, v.
Negative u, positive v, right? Okay, does that make sense? Because we're reflecting it over a vertical axis, is the movement of the point going to be horizontal or vertical?
Horizontal.
It's going to be horizontal, and so we'd expect the x's to be the things that change. The y's don't, right? Okay, so so what about this one here then? Let's look at this other case. What if we want to take the point G with coordinates 5, 4, and I want to reflect that in the line y equals 4? Okay, so where's the fold? What color is the fold in the paper up there then?
Blue.
No?
The y.
Yeah, kind of a lime green color, right? Does that make sense? Let's take a second and review that, because I think that's one thing that people sometimes have trouble with. If I want to come up with the equation of a vertical or horizontal line, they're the easiest ones by far, but they're not the ones we tend to focus on. We tend to focus on the harder slanted ones, right, with slopes and y-intercepts and things like that. Hey, do you want to grab your stuff? Yeah. So if if I want to name this line, what's the name of that line going to be?
P.
No, not P. I want to, like, it's not going to be y equals 3x plus 2. What do I name that thing?
X.
Anybody know? 2. Almost. Not
X
quite
equals
2. What equals 2?
X equals
X equals 2. Right? How come? Because, okay, it never crosses the y-axis, right? The slope is undefined. There's lots of reasons we can think about this, about why we might, lots of reasons for this. The main one is that every single point on this line has an x-coordinate of 2. The y-coordinate can vary. It could be anything. But the x-coordinate is always the same. And so that's what we name the line, by the thing that's going to be constant, the x-coordinate. Here's the rule, if you want to remember how to name these things. Ask yourself, if it's a horizontal or vertical line, you know that it's always going to be either x equals or y equals something, right? Which one is it? Ask yourself, which axis is cut by the line?
Y.
Which axis is cut by that line?
Y.
The x-axis is, right? Okay. The x, so you know it's going to be an x equals, and the number is just going to be where the x-axis is cut. It's cut at 2, so it's x equals 2.
I thought you were talking about the line. My bad.
No, I'm talking about this one. Okay? Now what about this guy?
Y equals 3.
Yeah, because the line is cutting the y-axis. It's horizontal. So it's going to be y equals 3, right? So what about this guy right here then? We've got a horizontal line, y equals 4. What's going to be the image of that pre-image, G? If I reflect it in the line, y equals 4.
negative
I asked you to grab your stuff. Grab your stuff. Really? Every time I look out there talking, I just get tired of that. Go ahead. Is 5-4. Yeah, it's the same point, isn't it? It's the same point. So it sits right on top. So it's both G and G prime. Okay, make sense? Okay, now, this is what we just talked about. Don't remember it this way. You're going to forget that. Just remember what we talked about. If something's reflected over a vertical axis, you know, if it's reflected over a vertical axis, all the motion is horizontal, right? And so it's the horizontal component that changes. If it's reflected over a horizontal axis, then only the vertical component is going to change, right? Okay. Reflection is an isometry. Just make sure that these pictures make sense to you. Just make sure that this, you know, this is, I'm sure they will, but when we reflect something simple like a segment over a line of symmetry, there's a couple different things that could happen. What if both endpoints are on the same side of the line? Then this is obviously what happens, right? Both endpoints get reflected over the line of reflection. What's going to happen? Try to visualize this in your head for a second. What's going to happen if one endpoint is on one side of the line of symmetry and the other endpoint is on the other side? In other words, the segment crosses through the line of symmetry. Okay, so yeah, in order for both of those endpoints to get mapped across that line, doesn't that mean that the reflection, that the pre-image and the image are going to have to cross? Right? Like that? That makes sense? The one place where the blue pre-image is actually on top of the line of symmetry, that point's not going to move, but every other point's going to get reflected across. That make sense? If one of the endpoints is on the line of symmetry but the other one's not, that's what would happen, right? What about that? If we're starting with the blue one and reflecting the blue one over the line, does that make sense? The red one's the result? Okay. Okay, so now lines of symmetry. Now this seems like a pretty minor deal, but this is a big deal.
Symmetry in math is really important. We use symmetry in math a lot of times to avoid having to do lots of work. It can replace tedious work. In calculus, for example, we're doing a lot of analyzing functions, using properties of the functions, calculus properties. And a lot of times what we're able to do is we're able to say, okay, now I know this function has certain kinds of symmetry. Maybe it has rotational symmetry about the origin. Maybe it's got reflective symmetry about either axis. If we know that stuff, then we can cut down the amount of work we have to do to analyze a function dramatically sometimes. We can take a small portion of the function and analyze that, and by using the symmetry of the function, we're able to fill in all the blanks without having to do more math. Yeah, go ahead. It's fast. You can do stuff, you're going to do stuff like this. For example, next year in Algebra 2, here's an example that you'll have to deal with. What if we want to graph a quadratic function? You guys have seen quadratic functions before. A quadratic function always makes this kind of U-shaped parabola, right, when you graph it. You're familiar with that?
Mhm.
Okay, if you want to sketch the graph of a parabola, all you really need to know to do that, as we're going to learn next year, is where the vertex is, and then where some point on one side of the vertex is, because the symmetry allows you to get a free reflection of that point. For example, let's just say that we found that the vertex was right there when we plotted it, okay? Here's our axis of symmetry for this parabola. So we know that this parabola is going to have reflective symmetry or folding symmetry about that vertical axis, right? All I've got to do is find one point on either side of that line, and we're like, say we found another point that sits on the parabola is right there. Then I can just take that point and reflect it over the line of symmetry over to there. And now I can use those 3 points to sketch the shape of the curve, right? Now that's a pretty minor example of how reflection, how symmetry comes in handy there. But there are lots of other ways too. In physics, for example, there are some bizarre kinds of symmetry that you wouldn't normally think of. Now, here's one of them. What about time symmetry? I mean, we can do lots of mathematical symmetries, but imagine this, and just imagine this situation for a second. Say I've got a ball, and I'm filming this. I'm going to throw the ball straight up in the air. It's going to go up in the air, rise to its highest point, and then fall back to my hand, right? Let's say I film that process, okay? Now, would you know, if I film that process, would you know if I show you the movie, if I've shown you the complete movie of the ball going up and coming down, or maybe I had shown you a movie of the ball going up, but then I just reversed I just spliced in a reverse, what do you call that? Backwards version of the movie. I ran the film backwards, the ball going up to here, and then running the film backwards, having the ball come back to my hand. Would it look any different? It'd look exactly the same, in fact. You wouldn't be able to tell the difference at all if you ignore air resistance. But even then, with it's going to be such a small factor that you can never tell by looking at it. You have to make some really accurate measurements. If you did it without any air in the room, there'd be no difference at all. Okay? And so symmetries they don't have to be things that are just about shapes. They can be symmetries in time. So we'd say that the ball going up to its peak and coming back down is symmetrical in time, right? It's the same process to go up forward in time and come down forward in time. So it would be to go up forward in time and come back down backward in time. There's no difference, right? So that's one kind of symmetry that we can exploit. It's not a normal one you think of, but that's a geometric symmetry too. It turns out that time is actually a part of this space-time continuum. So that's actually geometric too. Here's another one. I can't put my finger through this desk. If I try to put my finger through this desk, I'm stopped. And the main reason I'm stopped is because my finger's made of what we might call normal stuff, normal, ordinary matter, baryonic matter. Everything you've ever seen is made of that same kind of stuff. I mean, the desks, your light, all this stuff is all baryonic. It all obeys, it has certain types of properties and symmetries that it obeys. It can't be in the same place. One normal baryonic particle can never be in the exact same location as another baryonic particle at the same time. It's forbidden. That's why I can't put my finger you might be surprised to hear that most of the universe is actually not composed of this kind of normal stuff. Most of the universe is actually built from something called dark matter, which is not baryonic matter. It's different. It's bosonic matter. It's different stuff. And if my finger were made of that, I could easily put my finger through the desk and it wouldn't make any difference. Because one of the properties, the quantum mechanical properties of this other kind of bizarre matter is that particles of this, scientists call it dark matter lots of times, it can occupy the same place at the same time as another particle. There's no problem with that. And so it gets these weird properties. Now, one of the weird properties that comes out of this is you absolutely cannot see it or detect it. But this is the honest truth. If you hold your hand up and count to 5, something like 100 billion neutrinos have just gone screaming through your hand, and you would never know it though, because they're dark matter and they don't interact with the normal matter of your hand. But they do. They do all the time. We can detect these things. Science physicists can build these big massive detectors that can very rarely, they can catch an interaction between these neutrinos and normal matter. And the way they do this, they build these great big water tanks deep in mines, so all the other particles are screened out by the rock. And with these neutrinos just go whizzing through the earth like it's not even there. And so they interact every once in a while with the water in this tank, and they can detect that. But anyways, you know, it's a long story. But these things exist. 5 times as much matter in the universe is made of this dark matter than the normal stuff. And we know it's there because we can see that it affects the rates at which galaxies rotate, and it has these large-scale effects that are very measurable. So we've known about it for a long time, but it's just really, really hard to study or detect because it doesn't interact with anything. Question?
How does it actually
The thing is, it doesn't. That's the whole point. Is that that's why it's called dark matter, and why you can't really do much to detect it, because whatever you want to use to detect it, it's not going to interact with the detector. It just goes right through it. And so there is essentially only gravitationally does it interact with normal matter. So if you had a big lump of this stuff, it does have mass, and so it will gravitationally attract anything, but it doesn't interact in any other way. My point being, that's kind of a weird story, but that's what physics tells us. Physics is interesting. That this all has to do. The reason I bring this up, it all has to do with symmetry. Symmetry is not just as simple as you might think it is. It's not just things like this. I mean, you can take this whole idea of symmetry, and you can apply it to lots of other, lots of not so intuitive, not so obvious, parts of math and physics, and it helps us out a lot. Okay, but moving on, back to reality. Finding lines of symmetry. So you tell me now, real quick, why is that red line a line of symmetry for that hexagon? What do you think? Somebody hasn't answered yet. Somebody be brave here. What do you think? Okay, good. It cuts it into 2 congruent halves, doesn't it? One way of thinking of that is those 2 halves would reflect perfectly onto each other, right? They'd overlap perfectly. Are there any other lines of symmetry in that shape? And look carefully. No, in this shape right here, are there any other lines of symmetry? Seeing some no's. You're right. If you look closely, you can see, you might be tempted to think that maybe that's a line of symmetry, but it's not, because this point up here is a little sharper point than that is, and so they actually don't line up. It's kind of hard to see. They probably should have, when they made the bottom one go up like that or something. So they were obviously different. How about this one? Does it make sense that has 3 lines of symmetry?
Yeah.
Right? Does it make sense that has 6 lines of symmetry?
Yeah.
Because there's 6 different lines that could fold over on itself perfectly around, right? Can you think of a shape that has infinite folding symmetry, an infinite number of lines of symmetry? Circle, sure, yeah. Okay, all right. I think we're good.
Cycles.
I think you got the concept here. Let's
Cycles.